Today, the goal is to finish these notes and be done with our notes for the year, new information-wise, which is kind of crazy. But I think we can do it. I honestly believe in us, which would be amazing to have this done. So, get out your guided notes. I don't think so.
Oh, bruh. I've been gaslighted.
Why?
I've been told to get the chemistry up to next part.
Okay.
Are we doing the
Let's warm up with letter C. This is where I left off. So, I would like to know what is the voltage that comes from the net ionic equation and the voltage that comes from that.
Oh, we need a book, right?
Oh, crap. You need your book.
Right.
You know, I'll just give it to you.
Also, there's
Let's go.
There's the syrup and the if you flip the page.
Also, oh yeah, you're going to flip back. Flip back. You don't need it.
All of them are there.
They're all here.
Oh, bad.
So just use this.
Holy
I knew you did.
Is it A? With the negative chlorine? Or C?
We're doing C.
C, yeah. Copper.
Oh, we're just doing C. Which one is this?
So I want to know the voltage and the net ionic equation.
Step
Oh,
1.
I think I thought you said we're doing
Yes. Oh, copper.
C. F-E. So why are we doing C?
Because that's what I chose.
Oh, okay. Thank you for the clarification.
You don't have the guided notes packet?
When did we do notes?
We've done this. This would be like the third or fourth day we've done this.
On this week.
Okay.
So, what page is this on the book?
You don't need it. Just flip it back. A26 in the book.
Hey, cool. I got it.
Okay, you said we're writing
I want the net ionic equation and the voltage. And you might as well get the short form too.
Oh, look.
Oh my gosh.
Are we only doing C?
What?
Are we only doing something?
Yeah.
Does the cathode come first or short form?
Yeah.
Oh, it's anode.
No, anode, cathode.
So how do you tell which one's the cathode?
More the cathode is the more positive
Okay,
one.
cool.
Because it gets reduced.
Mm-hmm.
I remember.
He said cathode.
Oh, interesting.
There's mine. Do we match?
I'm not done yet, but.
Okay.
Erm.
Oh, I was looking at the wrong.
Guys, I think we got a problem.
Actually.
Oh, it's not in the book.
Oh, so you're saying you don't need the book? Oh, Peckwoods is my favorite pizza.
But
It's called Pequod's.
Call like a week in advance.
Oh, we should.
Pequod's, Pequods, best deep dish pizza you'll have in Chicago. Lou Malnati's, I don't like Lou's.
But that's the East right? The point something.
Yep. 0.78 is the E
It
sale.
was here. Oh, I do have that.
The what? Yeah, you gonna go see the bean?
I think it's under construction.
Oh.
How?
Oh, you could go see the rat hole.
Oh, yeah, I could go see the rat hole.
What's the rat hole?
There's like a rat-shaped hole in the sidewalk from where like a rat got stuck in the cement in Chicago, and like that was like tribute to it.
All right, are we good with this?
Yeah.
Okay. Electromotive force, E cell. E cell is the voltage. This is just kind of review what we've been talking about. Measured when no current is being drawn from the cell and is determined using a voltmeter. E cell can be calculated by using the following equations. When using this method, do not change the signs of the SERP values. So we've talked about this. E cell equals E cat minus E an, or E cell equals E reduced minus E oxidized, or E cell equals E right hand side from the shorthand version minus the E left hand side of the shorthand version. Those are all three versions you may see. The alternative is what I showed you up here, where you flip the oxidized half cell reverse sign and add the two up together. So a cell formed from a silver standard electrode and a hydrogen standard electrode generates a voltage of 0.80 volts. Hydrogen is the more negative electrode. So hydrogen is the more negative electrode. Write the cell diagram and calculate the standard potential of the silver electrode. So this one is one of those weird ones. Because remember, with hydrogen, you had to have the inert, like plutonium. Yes? So on this one, you start out with your plutonium, in parentheses, slash 1/2 H2, slash then your ion, H plus, slash back to your silver, Ag plus, slash Ag. And these are very easy to determine the potential whenever you're dealing with hydrogen, because hydrogen is always what? Zero. Hydrogen is what they were all based off of. So I just have to look up silver. Silver is plus, right here, 0.80 volts. I have nothing to subtract. So this is 0.80 volts. I'm going to write here because H is 0. So there's nothing to subtract. 2. When the silver electrode is combined with the standard aluminum electrode, the cell voltage is 0.24 plus 0.246 volts. Sorry, 2.46 volts. And aluminum is the more negative electrode. Write the cell diagram and calculate the standard electrode potential of the aluminum electrode. Okay, cell diagram is easy. The more negative one is going to be the one that is oxidized, therefore comes first in the short form. So it's going to be Al slash Al plus 3 slash Ag plus slash Ag. I know that the overall, or no, the overall is 2.46. So E cell equals E cat minus E an. So 2.46 equals, my cathode is silver, which we just had, is 0.80 volts minus X. So in order to get 2.46, that means that my answer is going to have to be a negative, right? In order to make 0.80 minus X equal 2.46? Yeah. Yes? So negative what? You can do this in your head. 1.66 volts. That is the aluminum, Al3 plus. Okay, more on electrolytic cells. Electrolysis is the process in which electrical energy is used to force. So we are leaving galvanic. What we've been doing the last 3 days, we're going to do our electrolysis, where we had to force a non-spontaneous redox to occur. So basically, the exact opposite. So this is the exact opposite of what we've been doing. It is extremely important to draw a distinction between galvanic and electrolytic cells. Electrolytic cells. Anions in the electrolyte solution are attracted towards the anode, where they undergo a process of oxidation. Electrons flow from the anode to the cathode, where cations undergo a process of reduction. Flip the page. Yes. So oxidation, anode, cathode, reduction. Okay. So one example would be the electrolysis of molten potassium chloride, which produces the following reactions. So here's the anode. So at the anode, I have chlorine, which is a liquid. Chlorine ion, which is a liquid. That makes 1/2 Cl2 gas plus an electron. Plus an electron. Yes. At my cathode, I have potassium ion, which is a liquid, plus an electron, yields potassium solid. So you can see the anode is doing what with the electron? It's gaining, yes? The cathode is losing. This is the exact opposite of what we've been doing the last 3 days. Yes? Yeah. So, the electrolysis of aqueous solutions are more complicated because water is also there. And water can also undergo redox. So you could also have something like this, where you have H2O, which is a liquid, making oxygen, O2, which is a gas, plus H plus. Now, if I'm balancing this, it's going to have to be a 2. This is going to be a 4, which means if I have a 4H plus, how many electrons does that have to give up? Plus 4 electrons. Plus 4 electrons. So the energy of this ends up being negative 1.23 volts. The cathode is reduction is gaining, right?
Yes.
In order to gain, you have to have the electron. Oh no, it is. It still is. Yeah, we just said it on the last page. It still is. So that's one. The other one is 2H2O liquid plus 2 electrons if it's going the other way. Yields H2 gas plus 2OH minus, which would be AQ. So this is negative 0.83 volts, because we know that water can be an acid or a base. So it can gain or lose. So you have this going on, which is in competition with what we just wrote. So I'm going to write that again. So it's still in competition with Cl minus, which is now AQ, going to 1/2 Cl2 gas plus an electron. And I still have my potassium, now AQ, because it's in liquid, which gives me, plus an electron yields potassium solid. So, when this is the case, decisions based on certain values must be made about the relative likelihood of one process over another. So here we go. Anode, cathode, I have a battery now because I have to have some kind of energy being put in to make this happen. Have to have some kind of energy being put in to make this happen. So if we're going to relate this back to delta G, K, and E, here's the relationship. The one we've learned so far is delta G, standard conditions, equals negative N, F, E. Yes, sorry. And we know Faraday's constant is the 96,500 joules per volt mole. And N is number of moles. Coupling this with delta G equals negative RT, natural log of K. Yes. If I combine these, I can make this into one big equation. And I end up with negative N F E equals negative RT, natural log of K. I'm just rearranging equations here. All right, we're not doing anything super crazy. I just set this equal to this because they're both equal to delta G. Also, if something is becoming more spontaneous, what happens to the value of delta G? It gets more negative. As I was grading the labs, there was some problems with that. Because some people said, it's becoming more spontaneous, therefore delta G is becoming more positive. No. Delta G is becoming more negative. I think that was actually mostly 5th period.
Wait, that lab was the one where you gave us like a little block of ice and then it melted on us.
Yes.
Alright.
Yes.
I wanted to make sure it was the right one.
It was that one. It's where you got to watch ice melt. Yeah. Flip the page. And the candle. Yes. And the candle. So here are your different scenarios. If K is greater than 1, your energy is positive, delta G is negative, it's spontaneous. So at equilibrium, products are favored, so therefore, it's going to move forward. If K is equal to 1, I have no energy, it's not spontaneous because it is at equilibrium. If K is less than 1, E is negative, so therefore delta G is positive, so my reactants are favored. So it's thermodynamically favored in the backward direction. That is why you have to put energy in to make it move forward. So this is galvanic, equilibrium, electrolytic. But what if conditions of voltages are non-standard? What if they're not standard? And this is not bad. All the calcs we've seen so far assume standard conditions, which are what? 1 ATM, 1 molar, and 298 Kelvin. When conditions are not standard, usually when they're different, so the things that are going to be different are going to be usually your molarity or your Kelvin. Your pressure doesn't change that much, but most likely they're going to change the molarity or the Kelvin. They could change the pressure, but different voltages than those predicted by the SERP will be generated in different cells. In order to make qualitative predictions about the changes these conditions cause, there's 2 ways to make a valid prediction. In order to make a quantitative prediction, there's only 1 way. So there's 2 ways for a qualitative. There's only 1 way for a quantitative. So we're going to do qualitative first, using only the reaction quotient. So going back 4 chapters ago, do you guys remember Q?
Yeah.
And what is Q?
It's what probably sort of the equilibrium.
It's
When you set the equilibrium expression, it's not at equilibrium.
correct. It's at another set of circumstances, right? Which makes sense because I'm at different conditions, which is why I'm using Q. So remember, a ratio of products to reactants is still raises their stoichiometric coefficients at any point of the reaction is called the reaction quotient. So if I was going to use the equation we've been talking about, if I still had my Cu plus 2, I'm going to write states, AQ plus Zn solid is in equilibrium with Cu solid plus Zn plus 2AQ. What would the Q expression for this be? So Q would equal concentration of Zn plus 2 over concentration of Cu plus 2. Solids are never part of equilibrium.
Why didn't you include the copper instead of gas? Oh, is that a gas or something?
This is solid. I got solid. Those are both solids.
I can't read.
Sorry.
I thought that's the copper gas.
Nope. It's a solid. Yeah, let me zoom in so you can see that that is clearly an S.
It does kind of look like a U.
But wait, hold on. Let me hold. See?
That's a gas.
That's an S. You guys can see the
That's a
S.
G.
There's no connection here for the G. Definitely solid.
That's.
Sure.
Definitely solid.
Actual impossible.
Now I feel better about that. In addition, the concentrations of the solutions, molar, mole per liter, partial pressures of any gases must also be included in Q. If you're doing Q with gases, you use parentheses. Don't forget that. Pure solids or liquids are not. Under standard conditions, concentrations are 1 molar and pressures are 1 atm. So Q always equals 1. But where the ratio is something other than 1, we must have non-standard conditions. Note, in cases like the reactions above, non-standard conditions such as 0.5 molar for both Zn plus 2 and Cu plus 2, if I make them both the same but less, Q still 1. Yes, Q still 1. Flip the page. So, why do values of Q not equal to 1? What do they mean for cell voltage? Well, qualitatively, here's what we think. When Q equals 1, there's no difference. So the cell voltage is described as having the standard value. When Q is less than 1, I have more reactants or a small concentration of products. This means increasing the driving force for the reaction. So the cell voltage is found to be greater than the standard value. If Q is greater than 1, I have more products or small amounts of reactants. This combination decreases the driving force of the reaction, and the cell voltage is found to be less than the standard value. So those are some just qualitative ways to think about that. If I use the reaction quotient and I compare it to the equilibrium constant, which is K, the equilibrium constant, I never make enough room to write this. Batteries eventually die. That is to say, the redox reaction in a cell is continually making its way toward a voltage of 0, right? Because if you think about an equilibrium, right, eventually they go to flat. In batteries, a voltage equals 0 corresponds to the equilibrium position. When the equilibrium has been achieved, a ratio of products, concentrations to reactants, is called the equilibrium constant, considered in the reaction. So if I use the same reaction again, I have my Cu plus 2, now I'm Aq, plus Zn solid, look at that beautiful S, is in equilibrium with Cu solid plus Zn plus 2 Aq. What's my K going to be for this? The K is what? It's the same, because it's still going to be concentration of Zn plus 2 over the concentration of Cu plus 2. This looks identical to the expression used for Q, but it's with one exception. Q can be calculated at any point during the reaction, whereas K can only be calculated once equilibrium has been established. So remember that K is only at equilibrium, or the end of the redox reaction. In thermodynamically favored redox reactions, the end will be achieved when large amounts of products have been produced and very few reactants are left, i.e. when K is large. At this point, the voltage in the cell is 0. Since at the beginning of the reaction, Q equals 1, the voltage is standard, then here's what happens. Any change in conditions that makes Q larger than 1, so if Q is larger than 1, that means we are closer to K, closer to equilibrium, closer to a voltage of 0, i.e. the voltage is less than standard. Any change in conditions that make Q smaller than 1 means that we are further from K, further from equilibrium, further from a voltage of 0, so the voltage is greater than the standard. So that's the qualitative way of thinking through this. I just wanted to talk through that, read through that again on your own sometime. Let's talk quantitative. Flip the page. I know, it just keeps going. So the Nernst equation, we're almost there. The Nernst. Anybody here know how to play Nernst, the card game?
No.
No, it's a good game. What we use for quantitative predictions of non-standard cells. The Nernst equation is used to calculate the actual voltage of a non-standard cell, and you guys have seen this partly. Well, you've seen all parts of this. So this is E cell is equal to E of my standard cell minus parentheses RT over NF. That should be probably capital F because that's Faraday's constant.
Oh, no, that's important.
Times the natural log of Q. So this is just combining everything we just talked about.
Bruh.
Yeah, NF. RT over NF times the natural log of Q. You know what all these are. So if Q is greater than 1, then the natural log of Q is a positive number. This means we're subtracting a term from the standard voltage, and therefore the voltage is smaller. If Q is less than 1, the natural log of Q is a negative number. This means we are adding, because minus a negative, we're adding a term to the standard voltage. Therefore, voltage is larger. If Q equals 1, the natural log of Q is 0. So we're not changing anything. So voltage is standard. Does that make sense what I'm trying to say here? I'm just showing you quantitatively, qualitatively what happens with those Qs. So here we go. If the reaction Zn plus Cu2 plus yields Cu plus Zn2 plus is carried out using solutions that are 5 molar zinc and 0.3 molar copper at 298 Kelvin, predict the effect on the voltage of the cell when compared to the voltage under standard conditions. What would be your first step on this?
Write out the equation.
We have the equation.
I'm not like the formula. You know, you're always supposed to write down the formula before you do problems.
What if we write out Q?
Yeah.
Okay. That's what you meant. Q equals concentration of Zn plus 2 over the concentration of Cu plus 2. So, they gave me both of these, yes?
Yeah.
So this is going to be 5 molar over 0.3 molar.
That's what.
In other words, this is what? 5 divided by 0.3 is what? Don't even do it.
5/3.
No.
It's big. Right?
No, it's not.
It's big. 5 divided by 0.3 is like 15 or something. Right? It's big. Yes?
15.
So if Q is big, right? What is going to happen to the voltage of my cell? If Q is going up big time, my voltage is going to be what? What we just talked about. Lower. Yes. So therefore, voltage is lower. Okay, a few other notes. We are almost to the last page. A concentration cell is set up in a half cell with the same metal electrode is present. The same metal, but solutions of the metal ions are different. Concentrations. When such concentrations difference, electrons flow from the half cell with the lower ion concentration to the half cell with the higher. Since electrons are flowing, there's a current and a cell set up. The electrons flow to the cell with a higher concentration of metal ions, where reduction takes place. And in the process of the ion concentration is lowered since the ions are converted to a solid metal. Since the lower concentration of the half cell is losing electrons, the metal electrode in that cell dissolves, producing more metal ions, and the ion concentration is increased. When the ion concentration increasing in the lower concentration half cell and decreasing in the higher concentration half cell, eventually the two cells will reach a point where the concentration of metal ions is the same in each cell. If they are the same, nothing flows. There has to be a potential difference in order for it to flow. An equilibrium has been established. In short, in concentration cells, electrons always flow in order to make and until the concentration of the two half cells have a potential difference of 0. Such cells generally produce quite small voltages, and calculations can only be carried out with the use of the Nernst equation. In other words, in lab, it's not a very easy thing to calculate. Did you guys do this in physics? No?
That went through 1 year.
Okay. You can read that on your own. This is it.
How do you explain it to me?
This is it. Quantitative aspects of electrolytic cells. The amount of a substance, here we go. We have like 8 blanks left. Produced in an electrolytic cell can be calculated using Faraday's law. F-A-R-A-D-A-Y'. Did I tell you what my big plan is for the summer? So, going to Tampa. Well, first of all, Memorial Day weekend, we're going to Pennsylvania with my in-laws. Getting home, I have to work the Tuesday after Memorial Day, which is ridiculous. That's teacher work day. Yeah.
I thought they tried to end it before Memorial.
For students, but the way it worked out, I have to come in one more day after Memorial Day. So does Emily's mom. Anyways,
Wait, what are you gonna do?
what am I gonna do that day? Well, teacher work day, I like shut down my room. Then we like have a luncheon, and then we have to like check out with our administrator.
We've done Okay, all right, sure. So you're doing nothing.
There's not much going on that day. Anyways, so then 2 days after that, I'm going to Tampa to grade AP test.
Yeah, that's fun.
You have some ideas for Tampa? I need ideas for what to do in Tampa.
Are we in the
It's
fourth
been a
grade?
while, but I can.
Okay,
think of
I'm
some.
gonna. The beach is not super close to like the convention center, but I'll probably go to the beach at least one day, using public transportation, obviously, since can't drive.
Well, hopefully you'll be able, did you say they might be able to, like,
That's him being optimistic.
That's my extremely
Okay.
optimistic side. My wife thinks there's zero chance, and her doctor father also thinks there's a very low chance of them lowering my sentence of 6 months of no driving. Not a sentence, sorry, but that's just what it feels like. Just
What do we do?
no, I didn't do anything. It's just like that's how it feels to me. So then the last week of June, we're going to the beach, and then the end of July into the first week of August, we're doing a two-week trip out west.
oh, are you going to Arizona?
We are going to do a lot of the national parks. So we're going to start at Indiana Dunes. Then from there, we're going to go to Rocky Mountain National Park. From there, we're going to drive to Dinosaur National Monument, which I've never been there. See some dinosaur bones. Then we're going to go to Salt Lake City. Since I've been there the last 2 years, grading AP tests, I'm going to show my family around Salt Lake City. Then from there, we're going to drive up to Jackson Hole, Wyoming. Hit the Grand Tetons. Yeah. Hit the Grand Tetons National Park. Then the next 3 days, Yellowstone. I can drive that day. That's my first day driving. Yellowstone. 3 days in Yellowstone. Then on the way out, we'll hit Devil's Monument. Then we'll go to Mount Rushmore, Badlands, a day of driving, staying with a friend in Chicago, back home.
Are you ever gonna make it on the road?
I don't know.
You should.
I am undecided at this point.
That is quite a trip.
Yeah. So, pretty epic. I was thinking about that since someone talked about Chicago pizza. That's been going in my head this whole time. All right. One method to calculate the number of Faradays, we've done this already. Pass electrolysis by using the following expressions. First, calculate the amount of charge Q in coulombs that's passed. So, Q equals I times T, where I is the current in amps. Current in amps. And we know that an amp is a coulomb per second. So if I take my I times T, that's going to cancel out your seconds. Second, convert the coulombs to Faradays. We know that a Faraday, actually I don't know if we talked about this, is equal to the charge in coulombs. And once again, it all comes back to Coulomb's law. Once again, Q, in parentheses, times there is 96,500 coulombs per 1 Faraday. Then you use Stoich. Then you use Stoich of the electrode process to determine the mass of the product formed at the electrode. We've done this already. This is just in words what we've already done. Remembering that a process that produces 1 mole of product by transfer of 1 mole of electrons will require 1 Faraday to produce that 1 mole, and that a process that produces 1, that should not say on, mole of product by the transfer of 2 moles of electrons will require 2 Faradays to produce that 1 mole, and etc. Here's an example. Yes. In the process below, 1 mole of copper solid can be produced from the reduction of 1 mole of copper ions by the passage of 2 Faradays, and a half mole of chlorine gas can be produced by the oxidation of 1 mole of chloride ions by the passage of only 1 Faraday. So here's those 2 half reactions. So the first one is Cu plus 2 electrons. That gives me Cu solid. And the other one is Cl minus Aq. It gives me 1/2 Cl2 gas plus an electron. When the number of Faradays is less or more than the required stoichiometric amount demanded by the half reaction, a simple proportion should be applied. So that proportion could be, 1/2, 1/3, whatever that might be, depending on your coefficients. That's it. That is AP Chem
Nap time!
2024.
All right, guys, good night.
Wow.
Good night.